In 4.1, we're going to look at quadratic functions and their transformations. We'll learn how to identify and graph quadratic functions. These functions come in two different forms, and the first one we're going to look at is vertex form. And this looks really similar to the absolute value equation, except instead of the absolute value bars, we have the parentheses and we have the squared up top. This squared is what tells us that we have a quadratic function. The a, the number we're multiplying by in front, is still our slope, but the a cannot be 0. Otherwise, it would get rid of that x squared portion. Then the graph itself, we call this a parabola. So this graph is going to be U-shaped, it has curved edges, and I can't emphasize this enough, but it is not straight. It's not like the absolute value, and it's not like a regular line. Here we have a picture of the graph itself, and we got all these points by plugging in different x values into the original equation and squaring them. And there's a couple features of this graph. First, we have the vertex. This is going to be the minimum or the maximum point on the parabola. Our vertex on this graph is found right here at the bottom. We have a minimum. Then the axis of symmetry. This is going to divide our parabola into mirror images, and it always passes through the vertex. If we were to draw a vertical line directly through our vertex, if we folded the graph along that line, the two sides would be on top of each other. They'd be mirror images. That means if we graph one half, if we know these points, we can just mirror them to the other side to get the other points. Lastly, we have our domain and our range. If we think about this equation, y equals x squared, domain is the x values. Can we square any number we want to, both positive or negative? Yeah, we can. So the domain is going to be all real numbers, and that's our symbol for all real numbers. Now we're going to look here at the range. Just looking at the graph and looking at all of our y values, we're going to notice that we have nothing that's happening down here where all those y values are negative. All of our y values start here at 0 and then continue to go up in both directions. So our range is going to be y is greater than or equal to 0. A quadratic in vertex form is still going to tell us the same transformations that an absolute value function did. The a, or the number that we're multiplying by, this tells us if we have a reflection, if we have a vertical stretch, or if we have a vertical compression. The h, or our inside value, is connected with the x, so it's still a horizontal change, meaning we're moving left or we're moving right. And k is outside where our y is, which causes a vertical change, so k can move the graph up or down. Just like with the vertex of an absolute value, it came from the h and the k value, the left and right, and the up and down. So our vertex, again, is going to be h and k. The axis of symmetry, same thing. It's always going to be x equals h. It's going to be the x coordinate of our vertex. If we have a positive a value, that means our graph is going to be opening up, and that causes us to have a minimum point. But if we have a negative a value, the graph is going to open down, which causes us to have a maximum point. So overall, h and k will help us find the vertex and the axis of symmetry, but then the a value will help us know if we have a minimum or a maximum. In our first example, we're going to graph using vertex form, and we have the following function we're going to graph. We know that it's going to be a quadratic, it's going to be U-shaped because we have that squared on it. Before we even get into graphing it, let's look at our transformation so we have kind of an idea of what it should look like. First, we have the negative. Remember, negatives cause the graph to flip over the x-axis, and when it flips, we call that a reflection. Then the 2 is going to cause the graph to stretch and get taller, so this is a vertical stretch. The negative 4 actually moves our graph to the right 4 units, and the positive 8 outside is going to cause it to go up 8 units. Looking at those transformations, that helps us with our first step, where we're going to try to find our vertex. Remember, our vertex comes from the inside and the outside number. So the vertex is at positive 4 and positive 8. Then our a is the number that we're multiplying by outside, which is a negative 2. Because of that negative and we have that reflection, our graph is going to go ahead and open downward. And we can start by graphing this on our graph. We're going to have the point 4 and 8, and we'll put that as our vertex. Next, we need to find the axis of symmetry. The axis of symmetry goes through the x-coordinate of the vertex. So it's going to be x equals positive 4. And we'll go ahead and draw that in as a dashed vertical line. This is the line that our whole graph is going to be symmetric about. What we do on one side, we have to mirror it to the other side. Now we just need to get some points on either side of our graph. So we can pick x values on either side of our vertex. The vertex was at 4, so let's just pick 3 and 2. But you could pick any x values you want. Next, we're going to plug these into our original equation. So we have negative 2 times x, which is now 3. Then the equation said we're going to subtract 4 and square it and add 8. Going through order of operations or plugging it into our calculator, we're going to end up getting an output or a y value of 7. We'll do the same thing with our other x value. We're going to do negative 2 times x, which is 2, minus 4 all squared, plus 8. This time we're going to get y is 0. These are the 2 points that we can now put on our graph. 3, 7, and 2, 0. Now we're ready for step number 4. We're going to plot the symmetric points. Our first point was 1 away from the axis of symmetry, so we're going to go 1 to the other side. Second point was 2 spots away, so we're going to go 2 spots in the opposite direction. Now that it's symmetric, we're just going to connect them with a nice smooth curve, making sure that our lines are curved and not straight, and we have the graph of our parabola. Example 2 looks at interpreting vertex form. First thing we need to do is identify our vertex. Remember that's coming from our inside number and the number we're adding or subtracting outside. We're going to change the sign of the inside, so we become positive 4, and the outside number stays the same, negative 2. The axis of symmetry goes through the x-coordinate of the vertex, so it's going to be x equals 4. To determine if we have a minimum or a maximum, we're going to need to look at that a value. And it's really helpful to draw just a quick little sketch of where our graph is situated. So we know it's at 4 for the x-coordinate and negative 2 for the y-coordinate, and we can put our vertex down there. Then when we look at that a value, since we have a negative, we know the graph's going to open down. So we can go ahead and just draw a little downward curved parabola. This helps us visualize and see that we do have a maximum point. And where does the maximum occur at? Well, the maximum is all about our y values. And at that max point, we're at negative 2. So we're going to have a max at negative 2. Then for the domain, we can plug in any number we want for x into any quadratic function. So the domain's always going to be all real numbers. But the range is going to change depending on where that vertex goes. Since the graph has shifted down 2, and since our parabola opens down, we're covering all of the negative y values. So y is going to be less than or equal to that maximum point of negative 2. Pause the video and give the next one a try. This time, since we have a positive a value, the graph's going to open up, which causes it to have a minimum value. That minimum still occurs at the y-coordinate, which is 1. And because the graph is opening up, our range is going to be y is greater than 1. We can also work backwards and write a quadratic function in vertex form. First, we need to identify the vertex and another point from the graph. Our vertex is at 1, 4, and another point that we have on our graph is at 5, 0. Then we're going to plug these back into the vertex form of the equation. So remember, our vertex is the h and the k value, and our x and our y from the other point take the x and y spot. This means 1 is h and 4 is k, x is 5 and y is 0. So we're going to have 0 is equal to a, that's what we're going to end up solving for, times x, which is 5, minus h, which is 1, all squared, plus k, which is 4. Using order of operations, we're going to have 0 is equal to a times 4 squared plus 4. So that means 0 is equal to 16a plus 4, and then we'll solve for a. Subtract 4 to both sides, negative 4 equals 16a, divide both sides by 16, and negative 1/4 is equal to a. Now we're ready for step number 4. We're going to substitute our a back into the vertex form of the equation along with our vertex. So we're going to have y equals a, which is now negative 1/4, times x minus 1, because that was the x coordinate of our vertex, squared, plus 4. Here is the equation to match the graph above. Pause the video and give this one a try. Remember that we're plugging it into the equation y equals a times x minus h all squared plus k, where the h and k come from your vertex, and the y and the x come from the other point. After plugging in your vertex and your point, this is the equation that you should get. Then you can solve for a, which is 4. Then we can substitute a and the vertex back in to get our final equation in vertex form.